Kari Eilola from SMHI, and I will discuss something about the biogeochemical cycles in the Baltic Sea. And I've just introduced the global ocean and put the Baltic into the context. And the idea here is to show surface layer nutrient maps of phosphate and nitrate in the global ocean. We have a scale ranging from 0 to 2.5 and 0 to 25 for phosphate and nitrate respectively. And if we look into the Baltic Sea, we see that the concentrations on a global scale are actually not very high, even though we also inside our region have gradients. For instance, in this case, surface layer inorganic phosphate. And usually we have enough inorganic carbon for this primary production of organic matter, and the nutrient limitation is mainly due to nitrogen, phosphorus and silicon. But in the world oceans we also have areas where production is limited not by nutrients, these purple areas, or not by nitrogen and phosphorus, but instead it's suggested that it might be iron that is limiting this production. And they call them high nutrient, low chlorophyll areas. And this is a typical figure of the ocean circulation, the oceanic conveyor belt. And if we look at the Baltic Sea, we have a similar conveyor belt, or the transport systems where we have shallow sounds connected to the North Sea and inflows with deeper or with higher salinity water that gets into the deeper parts of the Baltic Sea. And then we have internal circulation and horizontal transports within these sub-basins. And what's special about Baltic Sea is that, well, it's a semi-enclosed marginal sea, restricted water exchange, weak tides in here. And we have large freshwater supply, so we have low salinity. We have also low biodiversity. We have strong salinity stratification, shallow mixed surface layer and sea ice during winter, and we have also frequently anoxia in the deep waters because the mixing is very inefficient in the deep waters. We have a large nutrient supply, which causes the Baltic to become partly eutrophic, and we may also find widespread anoxia and large blooms of cyanobacteria in this area. If we compare the Baltic Sea with the deep ocean, what's striking is the difference in depth. Deep oceans have the order of 1,000 meter depth, while the Baltic Sea is of the order of 100 meter depth. If we look at the mixing depth, here is the thermocline. It's about 100 meter depth in the oceans, while it's only about 10 meters in this coastal area. And what's important here is that because it's so shallow, these sinking organic particles may reach the bottoms very efficiently in this area, and therefore the suspension and sediment fluxes becomes quite important here. Another factor is also different, is that we have large impact from colored organic matter, dissolved organic matter. And here is an example of the penetration of green light, 495 nanometers. In the clear oceans we have a penetration down to about 160 meters, while in our areas it's just of the order of 10 meters.
Could you explain that again?
Yes. This shows how large, this is the surface, so 100% of the light at the surface, and then we look how deep down do we find light in the sea. And in this case it's the green light, 495 nanometers. So in a clear ocean you can find light down, green light down to about 160 meters, with so 0.5% is still there. Where in our waters, coastal waters, you find the same amount of light at only 10 meters depth, so it's attenuated in the water and stays in the surface layers only because it's so turbid. So that's a really large difference. So how may climate impact on the biogeochemical cycling? So changed winds, for instance, because it's shallow, we may affect the bottom types in this area by resuspension. And if we have changed deep water formation, we can have changes in the supply of new water into the deep waters. We can have changes in the water temperature. We may have changes in the fresh water supply and the nutrient supplies, which also may cause changes in salinity and stratification and changes in sea cover, so in ice cover. So all these factors may have different impacts on the system. So now I will get into part of this conceptual ideas of biogeochemical cycling. And if we start with photosynthesis, we have this primary production of phytoplankton, and then we have transformation of carbon dioxide and inorganic nutrients to living organic matter, production of oxygen, and then we use phosphorus and nitrogen as essential nutrients in this system. So this is which I will focus on here. Nitrogen fixation will then also add more bioavailable nitrogen to the system. Then we have some driving forces here. It's supplies of nutrients, external supplies that are important. And then we have the internal circulation of these nutrients and some processing of the nutrients between inorganic and organic forms. We have some removal of nutrients inside the system. And what's not removed, it will become exported out from this system. So let's have a very simple model here. Just thinking, what do you think happens if we turn off all nutrient supplies to the Baltic Sea? There is nothing coming from atmosphere or land. In this case, the import of nutrients from the North Sea will become important. So instead of an export of nutrients, we will have an import from the surrounding seas. And the long-term net nutrient imports here will be balanced to the internal nutrient removal. So what happens if we have a closed ocean? We have a nutrient supply. So what will determine the long-term mean nutrient concentrations in the water here? And what if we don't have any internal removal? In the usual case, it is the internal removal will balance the nutrient supply, and the efficiency of this internal removal will affect the nutrient concentrations in here. This is a model experiment. In EcoSupport we had an ensemble of 3 different models, and if we look at this nutrient supply, we had about, and this is a 30-year control period, 1978 to 2007. We had annual nutrient supply of 835,000 tons of nitrogen every year, and 39,000 tons of phosphorus, and this is the biologically available nutrients that we are following here. And of these 835,000 tons of nitrogen, only 23,000 was exported, these tons. And of this 39, only 6,000 tons was exported.
Sorry, but how do you measure the biological available nutrients? What fractions do you use?
Good question. So when we add nutrient loads to the models, we have a total amount of, for instance, nitrogen that is coming from land and atmosphere. Especially from land, you have a fraction of that is organic nitrogen. And there is a question how large amount of this organic nitrogen is actually available for mineralization and cycling within this system. Another fraction is inert and just acts as a tracer. Somebody was talking about dissolved organic carbon here earlier. How large reactivity is it on that? And that's the same with nitrogen and phosphorus here. And for nitrogen, there is an assumption that about 30% of the organic nitrogen is bioavailable. So the rest is not used within the timescales that we have here. So there is an open question still. Good, but it's a good question.
And phosphorus?
For phosphorus, in this model ensemble, we had
100%.
Two models had 100%,
Yeah.
and one model had 50%. So there is a debate about this. Very good question. So anyway, from these budgets, can see that 97% of the supply of nutrients, external nutrient supply to the Baltic Sea, land and atmosphere, remains in the Baltic Sea. It doesn't go out from there. And 85% of this supply remains in the Baltic Sea. So this one is quite efficient. But if we look into in the same ensemble, we did these climate scenarios. And in the reference case, it's the first one was 78 to 2007, and the red one is now 2069 to 2097. And if we look at the nutrient supplies, there were fairly similar nutrient supply in these scenarios. We call it the reference scenario. But there is quite large difference in the export, especially when we look at phosphorus. So in this case, only 67% of the phosphorus remained inside the Baltic, and the rest was exported. So in the warmer climate, we had a less efficient internal removal of especially phosphorus. And now what I want to illustrate here is that if we don't remove phosphorus inside this system, it has to become exported out from the sea. And this means that we have to increase the concentrations of the water that is exported, because the physical export is approximately the same in the future scenario. So it means that we have to rise the concentrations in the surface layers to get out more phosphorus from the system. So in this way, the internal nutrient removal is regulating the surface nutrient concentrations and then also the primary production. And then inside this system, we have, of course, horizontal transport systems that when it comes to the surface, it is transported around rather efficiently within the Baltic, especially the southern parts. And then there are restricted water exchange with the northern parts. But it's quite efficient as well. So here is an example with our model where run it from 1850 to 2006, and then we have no internal removal of nutrients. So this means that all the supplied nutrients to the system has to be exported. And this is the river runoff of dissolved inorganic nitrogen and phosphorus that we are forcing the model with. It's fairly low numbers in the beginning of the last century, and then it increases after World War II, and then decreases in the recent times. And what we see in surface layer, this is from the central Baltic, East Gotland Sea, observations in red, and model results in blue. So if you look at nitrate observations, we find them around less than 5 at the surface layers. While in this case, with no internal removal, we would have more than 40. And this is the millimole nitrogen per cubic meter, or it's the same as micromoles per liter. And for phosphorus, it's more than 1, while we observe less than 1 in the surface layers. So the difference here is caused by the internal removal. So here I had this take-home exercise that you got earlier. It's just to think about. This is a very simple system. We have inflow and outflow, and we have supply from land to this system. We have fresh water and some nutrients in the fresh water. We have a given area and a volume of this system, some concentration and salinity. And then we have internal losses, this internal removal that I have been talking about here earlier. And then one may formulate a time-dependent equation here where we have changes in this concentration inside this basin depends on the supply from land and the supply from the outside ocean. And we remove nutrients from here by an outflow here and the internal losses. So it could be like a fairly simple Baltic Sea example. And
sorry, but I'm just a little bit confused. Are you including the fact that the Baltic has already nutrients in the sediments that?
in this case, we will only look at a steady state situation. So I will, for the exercise, we will do it very simple. So we will assume that this term is 0. So the time scales will get out of from this. And the only thing is that the internal, because the sediments on long term, as we saw from this example here, is that it removes nitrogen. It doesn't supply nitrogen or phosphorus to this system. It always removes on the net. Even if we on short term, say that you look on some years, there may be a net supply from the sediments because you make them anoxic. But on the average, if you look on long time scales, it's always a removal inside the system. So that's why we only have internal losses in this system. So in that way. And I just show briefly, how do I get there? That for your help. Now I have no glasses here. So task 1 is just to reflect on these equations, just to think about them. How will this system work? Here you have what is the steady state concentration as depending on the freshwater supply concentration in the freshwaters and so on. And you just think about what happens if this becomes large, this becomes small, or whatever. So you can get an idea how would this kind of system work. And the second task here is I also added point sources, because in this way we can use numbers from observations or the reconstructed loads from the Nest Institute, and you get some numbers and you can fill them into this steady state equation and examine how the concentrations will change for different cases. And I have also added an Excel sheet. So here one may just change the numbers here and you can get different concentrations. So this is a help if you want to have help with it. There is already an example inside an Excel sheet. So you just change the loads or you change the internal load efficiency and you get different concentrations. And then you can think about those numbers. So it's much just to understand about the functioning of this kind of system and the functioning of the internal losses. What does it make for the system?
May I ask something?
Yes?
What are point loads exactly?
Point loads. Okay, so you have, in this case we have Q0 is the freshwater supply, and then you have a concentration with nutrients in the freshwater. But then you may have cities or discharges directly from some cleaning, vad heter det? Reningsverk. Cleaning plants, wastewater plants, treatment plants and so on, going directly into sea. That's point sources.
Okay.
Yeah. So there's a difference. River runoff nutrients or directly loading from cities or treatment plants, others. So that's why I just added them, so you can have real numbers to compare with and think. You should, of course, and then there is this paper by Wolf and Stigebrand, and it's on this computer, where they have used actually this kind of formulation to study the Baltic Sea, different subbasins. Very simple example, but giving very lot of information. So now I will show some examples of our model results. And what we use here is the Rossby Center Ice Ocean model, and divides the Baltic Sea into 2 nautical mile horizontal and 3 meter vertical resolution. And we have a boundary here in the northern Kattegat. And for the global climate forcing, we have this downscaled, regional downscaling atmospheric forcing that was discussed by Eric yesterday. And we can have different global models. And in this case also one scenario, A1B, one emission scenario. So I will just briefly go through that. One example here. And then we have used this biogeochemical model that includes inorganic nutrients and 3 kinds of phytoplankton, including cyanobacteria that may do nitrogen fixation. We have zooplankton and detritus. And then we have a sediment compartment that includes nitrogen and phosphorus and transformations of those. Then including, for instance, denitrification and nitrification, burial, etc. And we have also resuspension of sediments caused by waves and currents. And I will discuss this reference scenario. So here is a figure showing vertically integrated, so sum up the transports of dissolved inorganic phosphorus in this case. And the arrows show the direction of the transports. It's the average for 30 years. And the colors show how strong transports are, so the magnitude. And then you have the black lines showing these contour lines are showing the streamlines. So following these streamlines are the transports. So what we can say from these experiments is that the nutrient transports generally follow the large-scale internal circulation of water inside the Baltic. And we saw also that there was only small changes of these circulation patterns in the future projections. So typical circulation is around the central parts east of Gotland and then around Gotland. And then you have also some internal circulation in the subbasins. And here is the same figure of dip but without the arrows. And then I have also included dissolved inorganic nitrogen, organic phosphorus and organic nitrogen as examples. And the difference between inorganic phosphorus and nitrogen is that maybe we can have some more impact from rivers along the coasts where we have major rivers. And when it comes to organic phosphorus, this is of course usually mainly in the upper part of the Baltic where we have the production and also where we have resuspension of sediments. So here we find also more concentrations, higher concentrations along the coasts. And since this is vertically integrated of course, the depth of the sea also plays a role. So these are the most deep parts. So there we have large transports of nutrients as well. Yeah.
Why is it so different between inorganic and organic nitrogen? Why do you have so much inorganic nitrogen there if you're expected to have a lot of primary production?
Because this is the annual transports in the system, and the largest fractions, if you integrate down to the seafloor, is actually in inorganic forms. So the organic forms are mainly in the surface layers, and since we do not have this background when it comes to nitrogen, if you look at the actual concentrations, you will have this passive or the non-reactive nitrogen part. So there is a large fraction that is not seen here, that is not involved in this biogeochemical cycling. It's just this like a passive tracer, large part of the nitrogen, and that's not included in this figure. Here is another figure based on these transports. We can then look at in each grid area, where do we find an import, net import of nutrients? Where do we have accumulation of nutrients? Or where do we find sources of nutrients inside this system? Where do we export nutrients from these areas? And this is also, again, inorganic nitrogen and inorganic phosphorus. Sorry, I was looking at the clock here. And if we look at the colors here, green means import. This means that we are bringing nutrients to this area. We are bringing phosphorus, inorganic phosphorus, to this area. While red color means that you are exporting phosphorus from this area. And if you look at the export parts, it's these deeper areas, especially along the slopes in the eastern parts of the Baltic proper, and in the Bornholm Basin, Arkona Basin, Gdansk Deep, and also inside the Gulf of Finland. And all these yellow areas are some also releasing phosphorus, but not so much. So these are areas where we have active sediments releasing phosphorus. And the green areas show where these nutrients are imported, and these green areas corresponds much to areas where we have an export of organic phosphorus. The red color here is export of organic phosphorus. So this is internal nutrient cycling. We have export of inorganic phosphorus from deep parts and imported to the shallow areas where we have production, and from there we have an export. And then we have an import of organic nutrients to the deeper parts. And this, I tried to make some numbers on this. So I summarized the import along areas that have the same bottom depth. So if we follow the 30-meter depth line here and calculate the import to this depth area in the model, and do that for each of the depths. So the red bars here, so if we go to 30 meter here, then we have a positive red bar. It means that at the 30 meter depth level we have a net import of phosphorus. While if we go to 100 meter depth level here, it's a negative red bar. This means that the 100 meter depth level usually, or the 100 meter deep areas usually export phosphorus. And then if we start to sum up these red bars starting from the surface, we see that the blue curve here is showing the sum of this. So all the way down to about 30 meters, we continue to have positive red bars. And this means that all 30 meter levels, and shallower than 30 meter level, they are importing phosphorus, while the deeper parts are exporting. And you see it on the red bars. And then we may compare it with the green one, which is the accumulated loads from land and atmosphere. So if we start summarizing all rivers and all atmospheric supply, we increase the green bar and get positive numbers. And at the end we see this is the total supply of dip to the Baltic proper. And what we can see is that the import to these shallow areas from open deeper parts is of the same order as the supply from land and atmosphere to this Baltic proper. Exactly what I was showing here, that deeper areas transport from these red areas, we transport dip to the shallow areas of the same order as the total supply from land and atmosphere. And then if we look at the climate impact. So here's the climate scenario as I showed you earlier. And if we look at this blue summarized one, we can see that it increases. The green is the loads, they were similar as we mentioned earlier, but the import to shallow areas increases. So the internal PS cycling intensifies in the future warmer climate, and we have an increased internal loading to these shallow areas, and the internal removal is much lower. That was also what we saw from the budgets. And if we look, if we have summarized all import in the end of this bar, the blue one is much larger. In this case, this means that we export much more to the other sea areas. So this old inorganic phosphorus is transported from deeper layers to the productive shallow areas. And the internal phosphorus cycling intensifies in future warmer climate, and we have an increased internal loading to the shallow areas. This was discussed in a paper from 2012 in Ambio. And then when we now know that future climate we will have more nutrients transported between different areas in the Baltic Sea, one would ask, where is this phosphorus lifted up to the surface layers? Is there regions where these increased loads of nutrients could have some, or especially phosphorus, could have some impact? So this was another paper. And here we used tracers, placed them below the halocline in the Baltic Sea, and checked where do we find these tracers after 6 months and after 1 year. And this is a period from 1960 to 2009, and it's the average for these periods. In occasions when we have no inflows, weak inflows and strong inflows. And the common pattern here is that after 6 months, after half year, we find these tracers usually along the coasts of Finland and Sweden. And the difference between this, if we have an inflow or no inflow, is that is stronger uplift during periods when we have strong inflows than others. And if we look after 1 year, where do we find this tracer after 1 year? This is at 30-meter level. I forget to mention, this is at 60-meter level, so it's just above the halocline. And this is at 30-meter level, it's just below the productive zone. So where do we find them? So much of these nutrients are found around the Swedish coast and south and east of Gotland. And it's a similar pattern in all these cases.
May I ask what happens in the Gulf of Finland? After 6 months there are lots of nutrients, but then after 1 year?
In this case, this is at the halocline. So it's lifted up to the water. But if you remember the transport, in the model we have these transport systems transporting nutrients this way. So when it's lifted up during this year, it's transported further on. And in this simple case, which I show here, it's just a passive tracer. But if we had biology included, maybe it could become used for production here when it comes closer to the surface or something like that. This is just an indication with tracers. So it's a indication of how it is transported in the model. Okay. See, 15 minutes. Shall we have 5 minutes now?
Yes.
Some air. Okay. Up and running. Welcome back. And I will continue now with something about regulating processes, I hope. And this is a figure that you can find in the back book. And I have also included sea ice here and resuspension. And all these factors has something to do with the biogeochemical cycling. And we start with the physical processes where we have this mixing with the halocline, permanent halocline in the Baltic Sea, seasonal thermocline, deep water renewal, and bringing in new water with oxygen into the deeper layers. We have the production part where we have the supplies with nutrients, both from land and atmosphere and also from below when we have regeneration of nutrients, remineralization. And we have the transformation of inorganic nutrients to organic matter and some export production of this organic matter into deeper layers, where we then find decomposition and mineralization that consumes oxygen. And you may also in anoxic areas have sulfate reduction and the nitrification. It's the use of nitrate for these decomposition processes. And this is one of the major sinks for nitrogen in the Baltic Sea. In the sediment, we have, as I mentioned, sedimentation of organic matter from this export production. We have some resuspension, bringing nutrients up into the water again, organic nutrients that may be transported to different areas inside the system. We have some transformations of NRP, nitrogen and phosphorus taking place in the sediment. We have for instance, binding of phosphorus to iron into sediments. And we may also have both permanent burial and denitrification. The question is then, how does internal nutrient cycling on the long term affect the removal of nutrients? This was what we were talking about earlier. How do all these processes affect the capability of this system to retain the nutrients, so we don't have to export them? Because if we have to export the nutrients, we will have to increase the nutrient concentrations at the surface and make more eutrophication possibly. So one way that we may regulate this removal is if we change the removal capacity of these permanent sinks. So if we change the nitrification, make it more efficient, we may remove more nitrogen. Or if we make the permanent burial more efficient, then we can get rid of more nutrients. Another way is to change the fraction of nutrients that escapes from these permanent sinks and stays in this pelagic cycling. So if we increase the decomposition of this organic matter, we may make a mineralization of it, we may keep them in the water. Or if we have a larger outflux from the sediments, or if we circulate the nutrients more fast in the surface layers, we keep them up there in this recycling between autotrophs, heterotrophs, bacteria, etc. So we keep them away from these permanent sinks. That's another way. And in all these cases, oxygen and temperature are important for the regulation of these processes. So if we look into the sediments, because this was a very shallow area, the sediments are quite important because large part of the production actually enters the sediments, either living organic matter or dead organic matter. So the dynamics of sediments becomes really important here. And if we look at these model results where we had an import of organic nutrients, this is where we have a possibility to put the nutrients into the sediments. And if we compare this with depth isolines here, we can see that this corresponds very much to deeper areas in these subbasins. So we may classify the bottom types into different areas. We have accumulation bottoms, and these you find very much in these green areas where we have this import organic matter. We may compare it with some different bottom types, like here we have bedrock, hard bottom, sand, hard clay and mud. So much of these muddy areas corresponds very well with these accumulation areas. Then we have transport bottoms where we have more or less temporary sedimentation of organic matter. And then we have erosion bottoms where we have very frequent resuspension of these sediments, so they cannot stay there for long. So they just fall down, and then there is activity lifting it up, and it continues to some more calm areas. So this creates our maps of different areas where we actually have possibility to accumulate nutrients from organic matter. And so how much nutrients will be there in the sediment? How much can you load? And this depends much on the temperature, because here are 3 examples. If we have a fast mineralization of the organic matter in the sediment, this is concentration in the sediment, and we have same sedimentation in each of these cases. Here is fast and a little bit slower and even slower mineralization. So in each case we get more nutrients in the sediments. And at this point I turn off the sedimentation, and then it's only mineralization acting, so there will be some kind of time scale for the decay of these nutrients in the sediment. Here I also have in this library, I can't see without my glasses. Sorry. Presentation. Let's see if it works. This is in some strange language.
What are you looking for?
I want to show visa here.
Yeah.
Let's try this one. No. I wanted to show all 3 at the same time. Visa. There is 3 different sheets, and I want to show them at the same time. So like
Switch this off. I don't know how this works.
okay, I can just go between these sheets, and they can explore them by themselves. But it was very illustrating when you have all 3 in the same.
You can load it again, and then
Yeah, let's try.
so you have more sheets.
Yeah, there are 3 sheets, and if you show, there is a possibility to make all 3 shown at the same time.
Should it be under Ansehen then?
And Licht. Okay. And then
Alle
open
Mann
out.
open.
Yeah.
Yeah,
This way
yeah,
or this way?
this way. Oh, yeah, very good. So, and then it's only this one, but maybe if I make this large. This one I want to have zoom like this one. No? This one? Yeah, no. There. And then I have in this sheet. So this is a simple sediment. We have the concentration is you have it's given by sedimentation, decomposition, and burial. So you have three components. Decomposition is described by temperature-dependent mineralization, and the burial is a constant fraction of how much you have in the sediments. And then there is one sediment assumption that we have 40 grams carbon per year, and then I have used this red fill ratio just to get nitrogen. And then we can experiment with the temperature and this temperature dependent. So if we set 0 degrees here, this is like the starting point. So if we look at the sediment concentrations at 0 degrees, and we have a certain mineralization temperature dependence, you might have like for this sedimentation a certain concentration in the sediment and a certain turnover time scale. It's 54 months in this case. And if you look in the lower graph, we see here is the sedimentation and here is the burial, and then this line tells us how many percent of the sedimentation is buried under these conditions. If we look into the end here, it's the steady state concentration. So this is just the change during time, and then after some time you come into a steady state concentration. And what happens if you get 10 degrees in the water instead of 0 degrees? Okay, more is mineralized from the sediments, so the concentrations in the sediments goes down. And if we look at this efficiency of burial, how large fraction of this sedimentation is buried, it goes down also. So here is a possibility to play around. And then we may also change the temperature dependence. So if we say now it's 0.15 per degree, let's say 0.07 for instance. So now it's less sensitive for temperature changes. So you can have more efficient burial of nutrients and the sediment concentrations changes. So this is something you have a possibility to play around with if you're interested.
How do you decide the sensitivity to temperature in a real experiment?
Yeah, let's go. I will continue if I can get there somewhere. Is it this one?
The second one.
No,
Is it
no,
Frölunda?
not that one.
This one.
Yeah.
Sorry, my language is. So later on I hope I will come back to that. But if we look into the Baltic Sea again, this is below 60-meter depth, and we look at the nutrient pools. In this case it's inorganic phosphorus and nitrogen, and we compare in this case with hypoxic bottom area. This means the bottoms that are covered with oxygen concentrations less than 2 milliliter per liter. What we see is that if we increase the area of hypoxia, we also increase the amount of phosphorus that we have in the water. If we look at nitrogen, on the other hand, this is the hypoxic water volume. So the amount of water that is hypoxic, we have the opposites, slightly opposite sign there, that the nitrification becomes more efficient if we reduce, if we have lower oxygen concentrations, more hypoxic water. So the reason here is that phosphate has the ability to adsorb to hydrated metal oxides in the sediment, for instance iron, and during oxic bottom water conditions. But when we go into anoxic periods, the retention of this mineralized phosphorus in the sediment is low, because it cannot attach to the iron during this anoxic period. And also it's a possibility that if we have adsorbed phosphorus earlier, this can be released from these iron bounds. I think there will be more discussions about sediments later on, and I will not go so much into details. And the denitrification is an anaerobic mineralization process that transforms inorganic nitrogen to dissolved nitrogen. So nitrogen gas is dissolved into the water. And this in turn requires oxidized forms of nitrogen. And what we saw in this case was that when we reduce oxygen concentrations in the water, we get more of this anaerobic mineralization processes taking place, and the nitrification increases. So we get less nitrogen in the water. But if nitrogen is depleted, if we don't have any nitrate anymore, then the nitrification will stop. So if we have long-term widespread anoxic areas, because in anoxic water we don't find any nitrate because we need oxygen to produce nitrate. And in these cases we might have that the efficiency of the nitrogen sink would become less efficient. So into seasonal cycles. This is driving much of the production seasons in the Baltic Sea. We have this mean incoming irradiance. This is the central Baltic with highest solar radiation during summertime, and of course highest summer temperatures and the building up of the thermocline, this productive layer at the surface of the Baltic Sea. And increased temperatures may strengthen this thermal stratification and also increase the length of this production season. And this may then affect the plankton composition. In this case it's illustrated by the chlorophyll A, and also the composition of what we can find in the water. So this is one of the climate effects. And another one is that if we start to produce more organic matter, this is Secchi depth, and this is mean Secchi depth in late winter and in summertime. So we see that there is about 5-6 meters difference in visibility of the water between these two seasons, and this is caused by more organic matter in the water. So if we produce more organic matter, we might have reduced transmission of light also. So this incoming light will stay closer to the surface. Yes?
Is that for coastal areas, or is that also it occurs in the Baltic proper as well?
This is the central Baltic proper, and this is taken from observations there. So, but if we assume that we, for instance, bring in more seed or colored dissolved organic matter with increased rainfalls, then we will have more organic matter in the water and change this visibility as well. So this was just to illustrate how organic matter can change the visibility, and this is just during the season. So it's like 5-6 meters difference just during 1 year. Another thing that is important in this context is the growth. So if we have a population X, assume it's plankton or bacteria or something like that, that is growing, usually we have some kind of proportionality to the population itself. So the larger the population, the faster the population grows. And this creates this kind of typical exponential growth curve, if this K is positive. If we make it negative, okay, this means like mineralization of organic matter, then we have a decay instead, and this also is proportional to the population, so we get this kind of exponential behavior. This is typical. But of course we don't have an infinite growth. Something is limiting it, and here I have used some kind of Michaelis-Menten type of nutrient limitation. So we have the green one is nutrients. They are taken up by the plankton that grow, and at some time the nutrients are depleted, and of course the growth stops. And in the other way, mineralization starts and we get nutrients back again. These are very fundamental. And this is from our model, how growth of phytoplankton takes place. We have some oxygen dependence, we have light limitation, nutrient limitation, and then we have the temperature dependent maximum growth rate of this phytoplankton, and here is the population. So this is the same equation as here, but more complicated. So in this case, the K includes more than just nutrients. And this, if we concentrate on this maximum growth rate, this is usually including some kind of temperature dependence. And here is an example. If we have something usually often used is temperature quotient Q10. This describes the ratio of activity for a 10-degree temperature change. So if we have Q10 is 2, this means that if we go increase the temperature 10 degrees, then the activity will increase with 2. Or if we have a higher Q10, like in this case 4.5, it will increase with 4.5 times the growth for a 10 degree. And this is, if you remember, I showed this Excel sheet and you asked me about these numbers. What numbers do you use for mineralization or for growth? So these are the kind of numbers that you can find in the literature if you look for QT for different species or different if it's soil or if it's in the water or in the sediments. But this means that in both these cases we have an increase of the activity. This means either the productivity or the mineralization if it's bacteria, or the productivity of bacteria. So this means that we have faster mineralization and faster oxygen consumption and nutrient cycling if we increase the temperature, just because of this temperature. And then depending on what is the sensitivity to this temperature change, that then determines how large the change is. Another factor that can affect this internal nutrient cycling is then the impact from deep water dynamics. This is exemplified here from the central Baltic. To the left we have, this is time from 1955 to 2006 or something like that. Salinity and phosphate and oxygen concentrations. And this is data from 150 to 190 meter depth. And what I want to show here is the negative correlation between phosphorus and oxygen. So during periods when we have anoxic conditions in the water, we have increasing concentrations of phosphorus in the water. And vice versa. When we have oxygen in the water, we have low concentrations of phosphorus in the water. And then if we look at nitrogen, here is green is nitrate and blue is ammonia, and then again the red one is oxygen. What we can see is that oxygen also affects quite heavily on the speciation of nitrogen. So during periods when we have oxygen in the water, we find nitrate because we need this nitrification. For the nitrification process we need oxygen. And during periods with anoxia, we usually only find ammonia. So what happens with these deep waters in the changing temperature in the future climate, for instance? We have an impact from air-sea gas exchange that is temperature dependent. And if we look at oxygen saturation, this means how much oxygen can the water take up from the atmosphere. This changes with temperature and salinity. So what is the situation? This water that is in contact with the air before it goes into the deep Baltic, it will have some kind of limitation. How much oxygen can it have? Of course, biological processes can affect it in some way, but the major part is the atmospheric exchange, and it's regulated by this. So if we look at 7 PSU, which is typical for central Baltic, in winter time we have about 2 degrees warm water, and then we see that it's about red here, so it means that we may have about 10 milliliters of oxygen in the water during winter. Then the temperature increases in the surface during summer. We may have about 20 degrees here. It's greenish, so it's only 6 milliliters per liter. So this is like the range that's caused by temperature changes at this salinity. So temperature change show 4 degrees, for instance, at S6 and T temperature of 2 degrees means 1 milliliter per oxygen less in the water, just because of the temperature effect on oxygen saturation. And this, however, the temperature impact is reduced when you have higher salinity in the water.
Can you go back on that?
Absolutely. So, and these formulations are available from the literature, because this is calculated in our model. So if we change the temperature here by 4 degrees, we will have automatically 1 milliliter less if the salinity is 6 of this water. Of course it's higher here, but as an example, it would be lower oxygen concentrations in the water that comes in. And then if you on top of that add increased oxygen consumption because of higher productivity and so on. So you will have several impacts on the oxygen conditions.
But at the same time, the salinity is expected to decrease?
I think that's there are some discussions about what the future changes that we have. What was the first salinity? What is the common conclusion about that? Can we say?
We will discuss on Saturday.
You will discuss it on Saturday. So okay. So salinity is a little bit more.
It's tricky. The uncertainty is rather large. There is some hint that there is a reduction in salinity because the runoff and precipitation is increasing, but there are other effects that may counteract.
So I will leave that open for discussions. But these are stuff that can affect the oxygen and the temperature, and these processes then affects this possibility to retain the nutrients in the or remove nutrients inside this system. Here is an example how stratification may affect. This is rather complicated, so I have to think about it. This is depths where we have observations of hypoxia and anoxia. So the blue dots show all depths where we have found hypoxic water, and the red dots show where we have found salinity higher than 11 PSU. And one thing here is that we may see during old times the blue dots with hypoxia were less high up in the water column than we can find them today. Usually we may also find them up to just below the halocline hypoxia, so just below 60 meters already you can find hypoxia during recent times. But then there is a period, I think I made a circle here, yes. that here that the hypoxia was found deeper down in the water column, and the reason for this was that during during a period of stagnation we had fairly large supplies of fresh water to the system, increased freshwater supplies, and during this period we have increased vertical mixing, so the deepening of this halocline, and that caused also had an impact on the oxygen concentrations in the water. So that's another very important factor that affects the oxygen in not only the inflows but also the vertical mixing. How deep down do we mix this surface layer water where we have good oxygen concentrations? So if we see here, it's digging down, deeper down into the Baltic Sea during this period because it's fresher and less dense water. And now I'd finalize with here is model results in red and observations in blue, and this is cod reproductive volume. This means, if we compare with this one, this means areas where we have oxygen higher than 2 milliliter per liter and salinity higher than 11 PSU. These are areas where we might have cod reproductive, where the eggs of cod may survive. And this was just a comparison of estimates from observations and from our model, and they seem to fit fairly well. So I will finish this presentation with a short movie, or long movie, I don't know. I run it from 1961 to 2007, and we see monthly mean values of model results, 2 nautical mile resolution, and here is of course the definition of this cod reproductive volume. So if you have more questions, please just come forward to me. I will be here until 4 today, and all this information you can find on this computer. So either if Brian sends it to you, or you take a stick and just take a copy of it, these Excel sheets, etc. And let's see if it works on this computer. So maybe I stop here and just... is this pause?
No.
No?
The big one first.
This one, yeah. Is it stopped? So what we see here is now we are already in 1963 in March, and it's the cod reproductive volume in cubic kilometers. So in each 2 nautical mile grid box, I calculated how large volume do we have where we could have cod possibility to cod for reproduction. And so we see each area here has a number. So red areas, there we have large volumes in this area, and blue or gray areas, there we have very low. So we can just see the evolution of this during this period. And if you have questions, please just ask. I will finish with this.
Okay, thanks a lot, Kari.
Thank you very much.